So hey friends, welcome back everyone. So here, I got a batch reaction problem for you guys. I've just noticed that I haven't been showing batch kinetics a lot of love. Most of the love has been going to CSTRs, PFRs, PBERs even. But hey, batch reactors are important. Like you find a lot of these in the pharmaceutical industries, guys. Like and in the polymers industry. So we're gonna focus on batch reactors for this video. Yeah. So just give the problem a read, like always. Okay, 1, 2, 3. I hope you guys have read the problem once, even twice, that's fine. The above esterification is supposed to be carried out in a batch reactor. Yay! Operating isothermally. I love these little cues. The following information has been given. So I have so this is the kinetics information. Okay, this right here is the kinetics info. And keep in mind we have a reversible reaction, just to point that out for you guys. So we have the initial concentrations of methanol and acetic acid. Before we proceed, in this problem, you have to decide which of these reactants is the limiting reagent. Yeah, GenChem's coming back to haunt you guys. So the limiting reagent in this problem is actually going to be acetic acid. Acetic acid right here. Right here, acetic acid. This is going to be my limiting reagent. Why is that? Please tell me in the comments below. Let's have some discussion going on. I hope those are the correct spelling. So acetic acid is going to be my limiting reagent. So I'm going to designate, the limiting reagent has to be designated as A. And methanol right here, I'm going to designate that as my species B. So if you're following Fogler, 5th edition, first 5 chapters, the species A always has to be the limiting reagent. Please review some GenChem if you have any questions. Alright, thank you. So, and once again, we have to model conversion versus time. Okay, time is the independent variable. Time is the independent variable when it comes to batch reactors. Alright, so let's see what we got. Assumptions. Isothermal. No change in temperature. Constant volume. We have a liquid phase reaction. Okay, aqueous reaction. Change in volume is going to be 0. Okay, good. Keep in mind we haven't assumed steady state. Why? Because it's a batch reaction. You can't assume steady state. Variables are changing with time. Come on. So mole balance on species A. Very good. But can we make it slightly simpler? I do know. Oops. Wrong pen. I do know that the number of moles Na is equal to concentration of A times the volume, right? I know that. And since we have constant volume, I can just pull this out of the derivative, right? And see what happens. Okay? Just some working ahead and boom boom. And hopefully this is going to help us. Okay, our mole balance has been slightly simplified by using one of our assumptions. All right. Okay, let's move on. So the rate law for a reversible reaction. Okay, nothing, we know K1. Okay, this is supposed to be K1, my bad. I know this. Alright, rate law. So I have the forward reaction, my reactants, and my products. Good. Okay, so but once I have the rate law, the next step is to look at the stoichiometry. Okay, I've done A here. Okay, I've done A for you guys already. So let's finish B, C, and D together. Let's switch around colors. Okay, we're gonna use pink for B. Ca0 times theta of B minus x. And theta of B is going to be, I believe it's going to be 2 over 5 or 5 over 2. So the initial moles of B divided by initial moles of A. It's going to be 5 over 2. 5 over 2. And it's a dimensionless number. For C, okay, let's move on to C. Ca0 times theta C plus x, and for D it's going to be Ca0 theta D. plus x. And in these two cases, theta c is going to be 0 because we are starting off with no products. Theta d is also going to be 0. No products initially. All right. Okay, so let's see. Now we're going to combine this with our rate law. If I remember, our rate law was the rate at which A is disappearing is proportional to CA. Okay, we have an expression for CA and CA naught. So I'm just going to work ahead a little. And hopefully I think that's going to give me CA naught squared times 1 minus x times 5 over 2 minus x. Okay, minus CA naught squared again. X. Hopefully I'm not. Let me use my brain power. Hopefully there's going to be an x squared here. Divided by kc. Okay. Alright, that does not look too bad. So we've combined the stoichiometry with the rate law. The next step is to combine it with the mole balance. And the mole balance was the rate at which the concentration of A is changing times the rate at which A is disappearing. And I know this, okay? That's right here. This entire expression is going to be substituted. This entire expression is going to be, I'm going to plug that in here. All right. Good, dCA dt. We're just figuring this out. Okay, 1. Okay, I'm just gonna, let's see if I can do some one note magic. All right, patience is the key. There we go. All right. Bad boy. Oh, it works. It worked. There we go. I would prefer it worked faster, but this is fine. And also, are we missing something? Oh yeah, I have my independent variable as the concentration, whereas I want my differential equation to be the dependent variable to be the conversion, right? And I remember that CA is just equal to CA naught times 1 minus x, right? Which means that dCA is going to be equal to negative CA naught times dx. All right. So with that in mind, my original differential equation, let me just copy that. My original differential equation is going to become, give me 1 second. Copy that again. Paste it here. Oops. Sorry about that. Paste it here. All right, very good. Patience is the key, right, boys and girls? Right. So this is just going to become dCA can be replaced by negative CA naught times dx. All right. And if you want to do the next step in the algebra, dx dt is going to be all of this, k1 times, I'm going to skip some steps now, CA naught times 1 minus x, 5 over 2 minus x, minus CA naught x squared, divided by kc. The next step is to integrate. All right. The next step is to perform the integration. Now, at first sight, this might look like this differential equation is most certainly a separable ODE, but the integration is going to be not very nice. So we're going to perform numerical integration for this in the next part of this video. All right, we're going to be using numerical integration in the next part of this video. All right. So thank you so much for sticking around till the end. Once again, once again. All right, assumptions. All right, I'm not assuming steady state. Mole balance. All right, the rate at which the concentration of A is changing. All right. Okay, the rate law. Very good. Stoichiometry. All right, stoichiometry. And then we combined everything. First I combined stoichiometry with rate law, then we combined rate law with the mole balance. I did some algebraic manipulation on the mole balance. And now to integrate this, we're gonna have to refer to numerical techniques. All right. Thank you so much for watching.